In this video, we'll go over LeetCode question number 322, coin change. Now, if you haven't seen my video on LeetCode question 70, climbing stairs, I highly recommend you watch that first. Coin change is a very similar problem to climbing stairs, but it's harder. The link is in the description, so please go watch that first. Okay, so now let's look at the problem. Given an integer array coins, representing coins of different denominations, and an integer amount, we need to return the fewest number of coins needed to make up that amount. If it's impossible to make that amount, then we'll need to return -1, and we can also assume that we have an infinite number of each type of coin. For example, let's say the coins array consists of 1, 5, 10, and 25, and the amount we need to make is 68. The answer would then be 7, because we could use 2 25 coins, a 10 coin, a 5 coin, and 3 1 coins, and it's impossible to do any better. Now, the most intuitive way that most people would think of is to use a greedy approach. In this case, this means we would start by using the coin with the highest denomination and then work our way downwards. For example, using the same example as before, let's start with a total of 68. And since 25 is less than 68, we can use a 25 coin, and then another, and now the remaining amount is 18. Since 25 is greater than 18, let's move on to the next largest coin, which is 10. The remaining amount is 8, so we'll use a 5 coin next, and then the last remaining 3 will be taken care of by 3 1 coins, and now we finally hit 0. And as you can see, we used a total of 7 coins. Now, this approach worked for this example, but the problem is it doesn't always work. Let's look at another example where the coin denominations are 1, 7, and 9, and the amount is 21. Using the greedy approach, we'd start by using the 9 coin, and 21 minus 9 is 12. We can then use another 9 coin, and the remaining amount is 3. We can't use the 9 coin or the 7 coin, so we'll fill the remaining 3 with 3 1 coins. So according to the greedy solution, the fewest number of coins is 5 coins. However, the correct answer is actually 3 coins, since we could have just used 3 7s instead. So this is an example where the greedy solution failed. So how do we solve this problem? Well, one way to solve this is to just use brute force and calculate every possible combination of coins using recursion. Here's the idea. We'll start by using one of each coin and subtract it from the total. So for each coin, we'll calculate the remaining amount if we use that coin, which will be the total amount minus the value of that coin, and we'll do this separately for each coin. If the remaining amount is still greater than 0, then that means we need to use more coins, and we now need to figure out the fewest number of coins needed to make the remaining amount. And so we'll do that by recursively calling the same function again, but this time pass in the remaining amount, and this will keep recursing until we hit 0. So let's visualize this with a simple example. Let's say the only 2 coins we can use are 1 and 3, and the total amount is 6. We'd start by making 2 recursive calls here. One of the calls will assume we started by using a 1 coin, so we'll subtract 1 from the total, and call the same function again, but pass in 5 as the new amount. So we're now trying to find the fewest number of coins needed to make a total of 5. On the other side, we'll assume that we used a 3 coin to start, so we'll subtract 3 from the total, and recursively call the function with an amount of 3. So here, we're trying to find the fewest number of coins needed to make a total of 3. Let's recurse down the left branch first. From a remaining amount of 5, let's subtract 1 and pass in 4 to the new function. We'll also need to try subtracting 3 and pass in 2 to the new function. And we keep going. From the amount of 4, we'll try using a 1 coin, then a 3 coin. And from the amount of 2, again, we'll use a 1 coin, then a 3 coin. But now notice something. When we tried to use a 3 coin on an amount of 2, we ended up with -1. This means we overshot the total, so now we know that using a 1 coin, 3 coin, and another 3 coin leads to a dead end, so we can stop recursing on this branch. Let's continue with the other branches. From a total of 3, let's use a 1 coin, then a 3 coin. But now notice that the remaining amount has hit 0. That means we finally found our first solution, which is to use a 1 coin, 1 coin, 1 coin, and then a 3 coin. We still need to explore the other solutions though, so let's keep going. From a total of 1, let's use a 1 coin, and now we've hit another solution, which is to use a 1, 1, 3, and a 1. Notice that this is actually the same answer as before, but the coins are just in a different order. Next, using a 3 coin leads to -2, so that's a dead end. And here we see the exact same thing happening. Now let's finish the far left branch. 2 will lead to 1 and negative 1, so that's a dead end. And the last call will lead to 0 and negative 2. And now we found the fourth solution, which is to just use 6 ones. Now let's finish the right branch. 3 will lead to 2 and 0, and so our fifth solution is to use 2 3s. The remaining amount of 2 will lead to 1 and negative 1, and 1 will lead to 0 and negative 2, and that is our sixth and final solution. Now that we've gone through the entire recursive tree, we can see that the optimal solution is to use 2 coins, a 3 coin and another 3 coin. This works, but the problem is, if n is the number of coins and m is the amount, in the worst case, this tree will have a height of m and each node will have n children. So this runs in O of n to the m power time. So why is this so inefficient? Well, let's take a closer look. Notice that we're calculating the fewest number of coins to make an amount of 1 4 different times. We're also calculating the fewest number of coins to make 2 3 times. And we're doing the same thing for an amount of 3. And notice that we go down the exact same recursive branch each time. So this is where the redundancies are. We're calculating the same thing over and over again and making a lot of unnecessary function calls. We also go down this very inefficient path of using 6 1 coins, when really, by the time we got to the third coin, we should have just stopped here and realized that we could have used a single 3 coin instead. So we're going to make this more efficient by using dynamic programming to calculate the fewest number of coins to make a certain amount only once, and then reuse those values to build our solution. As usual, dynamic programming can be done either top-down or bottom-up, but since the bottom-up approach eliminates the recursion entirely, that's what I'll be focusing on in this video. So here's what it looks like. Using the same example as before, we'll first create an array that goes up until index 6, which is the amount that we are given. In this array, each element will contain the fewest coins needed to make an amount of that index. For example, the element at index 3 should contain the fewest number of coins to make an amount of 3. We start by putting a 0 at index 0, because you need 0 coins to make an amount of 0. Then let's figure out how many coins we need to make an amount of 1. If we start by using a 1 coin, then the remaining amount is 1 minus 1, which equals 0. So the next question is, how many coins do we need to make an amount of 0? To figure that out, we can look at the element at index 0, and we see that we need 0 coins. So the total amount of coins is the 1 coin we used initially plus 0 coins. So the total number of coins needed comes out to 1. We can't use a 3 coin yet because the amount is too small, so let's move on and figure out the number of coins needed for an amount of 2. If we start with a 1 coin, then the remaining amount is 2 minus 1, which equals 1. So now the question is, how many coins do we need to make an amount of 1? And as you can see, we already calculated that, and the answer is 1. So by using a 1 coin initially, then using another 1 coin to make up the remaining amount, we'll need a total of 2 coins. We still can't use a 3 coin yet, so let's move on to index 3. Again, we'll start by using a 1 coin, and the remaining amount is 2. So how many coins do we need to make an amount of 2? And again, we already calculated that here. So we'll need a 1 coin to start, and then 2 more 1s to make up the remainder. That's a total of 3 coins. But wait, now that the index is finally 3, we can start using the 3 coin. So what happens when we start by using a 3 coin instead? Well, 3 minus 3 is 0. So how many coins do we need to make the remaining amount of 0? And the answer is 0. So now we found a way to make the total by using less coins. We can use a single 3 coin to start, and then 0 more coins are needed. So we only used a single coin. Since 1 is less than 3, we'll overwrite the value at index 3 with 1, which represents using a single 3 coin to make the total. And it's the same idea for the rest of the array. We subtract both coin denominations from the amount we're trying to make, and we use our dynamic programming array to reuse the previously calculated number of coins instead of recalculating them over and over again. So for index 4, starting with a 1 coin, the remaining amount is 3. As we just saw, the fewest number of coins needed to make an amount of 3 is just 1. So we'll need a total of 2 coins here. Then we'll try using a 3 coin first. The remaining amount is 1, and we need 1 coin to make an amount of 1. This is the same answer with just a different order of coins, so we'll leave it at 2. Next is index 5. 5 minus 1 is 4, and we'll need 2 more coins to make up the rest. So the value at index 5 is 2 plus 1, which equals 3. Then we'll try 5 minus 3, which is 2, and we still need 2 more coins. So the value at index 5 stays at 3. We're finally at the last index. 6 minus 1 is 5, which corresponds to 3 coins. So we could use 4 coins to make an amount of 6. But if we start by using a 3 coin first, then the remaining amount is 3, and we see that we only need a single coin to make up the remaining 3. That's a total of only 2 coins, so let's rewrite this value to be 2. And we're finally done. All that's left to do is return the value at index 6, which is 2, and we have figured out that we only need 2 coins for this problem. The difference here is we only had to traverse an array of length m plus 1, and for each one of those elements, we had to loop through the array of coins, which has n elements. So in total, the dynamic programming approach runs in O of n times m time, which is a major improvement. Now let's look at the code and try an example using Python. Let's say the coins are 1, 2, and 4, and the amount to make is 7. We'll start by creating our dynamic programming array, which I'll call dp. This array needs to go until index 7, so it needs 8 elements. And this right here is kind of a cool Python way of doing it. So we're first going to create a list with just 0 as its only element, and then concatenate that with a list of length 7, and fill it with infinity, so it looks like this. If you're not familiar, this is a cool way you can represent infinity in Python. It's guaranteed to be greater than any number when used in comparisons, and adding and subtracting any number from infinity still results in infinity. You'll see in a second why having an infinite value is useful here. Next, we're going to iterate through the array starting at index 1 using the variable I. We also have an inner loop, which is going to iterate over the coins array using the variable coin. So for each index, we're going to try subtracting each coin amount from that index. But before we subtract the coin from the index, we'll first check that the coin amount is less than or equal to the index. Otherwise, we'll end up with a negative number and go out of bounds. Right now, I equals 1 and coin also equals 1, so we can proceed. Now let's break down this line a bit more. First, let's look at the element at index I minus coin. In other words, this is the remaining amount after we use the current coin. Right now, I and coin are both 1, so I minus coin is 0. The element at the 0th index of the array is 0, so this value here is 0. We're then going to add 1 because remember, we just used the coin and subtracted it from I, so the total number of coins needed to make an amount of 1 is 0 plus 1, which equals 1. We're then going to compare that to the current element at index I, which is initialized to infinity. We're then going to take the minimum of those two values, and that's going to represent the fewest number of coins needed to make an amount of index I. So that's why we initialized all those values to infinity. It guarantees that it'll always get replaced by the first solution found to get us started. So since 1 is less than infinity, the element at index 1 will be 1. Now let's look at the next coin, which has a value of 2. 2 is greater than 1, which means we can't use this coin, so we'll just skip it. The next coin has a value of 4, which is also greater than 1, so we're done trying all the possibilities for index 1, and we can move on to index 2. We'll start from the 1 coin again, and 1 is less than 2. So let's find the element at index 2 minus 1, which is 1. So you need 1 coin to make an amount of 1. If we include the coin we just used, then 1 plus 1 equals 2, and 2 is less than infinity. So let's write a value of 2 at index 2. Then let's try the next coin. 2 is equal to 2, so we can use this coin now. The element at index 2 minus 2 is 0, and 0 plus 1 equals 1. 1 is less than 2, so we found a way to use a fewer number of coins, which is to just use a single 2 coin. So let's overwrite the element at index I to be 1. Next, 4 is greater than 2, so we'll skip that for now and move on to index 3. Then we'll do the same thing. 3 minus 1 equals 2, and the value at index 2 is 1. 1 plus 1 equals 2, so let's write a value of 2. For the next coin, 3 minus 2 equals 1, and the value at index 1 is also 1. So either way, we have to use 2 coins, so let's leave this at 2. The 4 coin is still too large, so let's move on. 4 minus 1 is 3, and we need 2 coins to make that amount. So we'll start off by writing a value of 2 plus 1, which is 3. Next, 4 minus 2 equals 2, and the value at index 2 is 1. 1 plus 1 equals 2, which is less than 3, so let's overwrite this with 2. We can now finally use the 4 coin, and 4 minus 4 equals 0. 0 plus 1 equals 1, which is less than 2, so finally we overwrite this with 1, since we only need a single 4 coin to make a total of 1. Next is 5. 5 minus 1 is 4, which corresponds to 1, and 1 plus 1 equals 2. Next, 5 minus 2 is 3, and the corresponding value is 2. 2 plus 1 equals 3, which is greater than 2, so the value at index I stays at 2. Lastly, 5 minus 4 equals 1, which corresponds to 1. 1 plus 1 is equal to 2, so the final value stays at 2. For index 6, first we'll check the value at index 5, which is 2. So let's start with 2 plus 1, which equals 3. Then we'll check the value at index 4, which is 1. And 1 plus 1 equals 2. So let's update this to a value of 2. Lastly, the value at index 2 is also 1, so nothing changes. We're now at the final element, which is going to be our final answer. If we start by using a 1 coin, then we need 2 more coins to make up the rest, so we start with a 3. If we use a 2 coin, then we also need 2 more coins to make up the rest, so that's not any better. And lastly, if we use a 4 coin, we still need 2 coins for the rest. So now we know that we can't do any better than 3 coins, and we're finally done with the loop. The only thing left to do is to return the value at the last index. The problem also wants us to return -1 if there is no answer, so we have to add a bit of extra logic at the end. If the last element of the array is still infinity, then that means we weren't able to find any combination of coins to make that amount. So in that case, we'll just return -1. And I'll do a quick example of this at the end. But right now, the last element of the array is not infinity, which means we have a valid solution, and we can just return that value. So the fewest number of coins needed to make an amount of 7, using the coins provided, is 3 coins. So we return 3 and we're done. Now to wrap this up, I'll do a quick example where there is no solution. Let's say the coins array is just 2 and 4, and the amount is 5. We'll start the same way as before by creating the DP array and begin iterating at index 1. The first coin is 2, and 1 minus 2 is -1, so we can't use that. 1 minus 4 is -3, so we can't use either coin to make an amount of 1, because they're both too big. So in that case, we just move on to the next index, and the value at index 1 stays at infinity, which means that it is impossible to make an amount of 1. For index 2, we could just use a single 2 coin, and we would need 0 more coins after that, so let's put a 1 here. 4 is still too big, so let's move on. For index 3, if we use the 2 coin, then there would be an amount of 1 left over. So how many coins are needed to make an amount of 1? As you can see, the value there is infinity, since it's impossible to make an amount of 1. So 1 plus infinity is still infinity, and the element at index I is also infinity. The minimum of infinity and infinity is infinity. So the element at index 3 stays at infinity, since we can't make an amount of 3. We still can't use the 4 coin, so we move on. 4 minus 2 is 2, which corresponds to a value of 1. 1 plus 1 equals 2, so let's write 2. Next, 4 minus 4 equals 0, and 0 plus 1 equals 1, so let's overwrite this with 1. Now we're finally at index 5. If we start by using a 2 coin, then we have an amount of 3 left over. Since there is no way to make an amount of 3, the value stays at infinity. What if we used a 4 coin first? Well, 5 minus 4 equals 1, and there is no way to make an amount of 1 either. So we can't get the value at index 5 to be any less than infinity, and the loop just ends. Now when we get to this condition, the value at the last index is infinity, which means that a solution could not be found. So we'll just return -1, and we're done.